All right, welcome back to Engineering Systems. So in our last explainer, we really dug into strong consistency. The idea that your data has to be correct, everywhere, instantly. It's the absolute foundation for systems that just can't afford to be wrong. But what happens when you need to go global?
Today, we're going to flip that whole idea on its head. We're stepping into a completely different philosophy, one that actually powers the massive worldwide applications that we all use every single day. We are talking about eventual consistency.
And you're going to see exactly why this isn't some kind of flaw or a bug. No, it's actually a critical feature that allows services, from your social media feed to huge e-commerce sites, to feel incredibly fast and responsive no matter where you are in the world.
And we're also going to break down the very deliberate compromises that engineers have to make. See, this isn't about just accepting flaws. It's about making really smart trade-offs to achieve mind-boggling scale and availability.
Look, this is a core concept, a real cornerstone of system design. So if you're following along with us to really get a grip on how modern systems are built, go ahead and hit that subscribe button. You're not going to want to miss a single step.
Okay, so let's get to the heart of it. What on earth is eventual consistency? And maybe more importantly, why did we even come up with it in the first place?
So here's the textbook definition. Let's really chew on that for a second. The system is not promising to be correct right now across all of its copies or replicas. Instead, it just makes a promise. If you stop making changes, they will all eventually catch up and agree on the same state.
So did you catch what's not being said? The big missing piece is when. There's no guarantee of how long it'll take. For a little window of time, different users in different places might actually see slightly different data. And that's not an accident. That's the whole point. So why would we ever design a system like this? Because the real world is an absolute mess. It's not some pristine laboratory. Networks get congested, whole data centers go offline, an undersea cable gets snipped. Machines just die. Strong consistency often needs to wait for everyone to agree. And that can bring the whole system to a grinding halt when one of these things happens. Eventual consistency just says, you know what? We're not waiting. We're going to keep moving. So this is the crucial point right here. We are making a choice. We are choosing to keep the system up and running, that's the availability, and making it feel incredibly responsive to users, that's the speed. And we're doing it by relaxing the need for every piece of data to be perfectly in sync, everywhere, all the time.
Okay, theory is great, but let's make this concrete. And there is no better way to understand this than with an example you probably interact with dozens of times a day, the social media like button.
So let's trace the journey of one little like. When you tap that button, your request flies to the nearest data center. Let's say it's in Virginia. It updates its local count and immediately tells your app, success. You see the number tick up. It feels instant, right? Then, in the background, without making you wait, that Virginia server starts gossiping, telling all the other data centers around the world about your like.
And this is the direct result. For a brief moment, your screen in the US might show 101 likes, while your friend's screen, which is connected to a data center in Japan, still shows 100. Their server just hasn't gotten the memo yet. This right here is that temporary disagreement we've been talking about, out in the wild.
But here's the real question. Does it matter? For a like counter, absolutely not. No money is lost, no critical operation fails. What you get in return is that instantaneous, snappy user experience. The system feels fast, and for this use case, that's a trade-off we will gladly accept all day long.
So let's formalize this a bit. Just like any big architectural decision, choosing eventual consistency comes with a balance sheet. It's got some really powerful benefits, but also some very real challenges and hidden costs.
I mean, the pros column is a powerhouse. You get high availability because one offline server doesn't take the whole system down. You get incredibly low latency writes because you aren't waiting for global consensus, and that lets you scale to massive audiences. On the cons side, though, you have those stale reads we just saw. But more subtly, you introduce a ton of complexity, and it forces developers to think in a completely different way.
This quote just nails what I call the psychological cost. The system no longer guarantees correctness for you. That entire burden gets shifted onto the developer. You now have to actively write code for a world where data might be slightly out of date, or where two users might update the exact same thing at the exact time. You have to design for convergence, not just for immediacy.
So, given all these trade-offs, it's critically important to know where the buck stops. When is this model not just a bad choice, but a downright dangerous one?
You would never ever build these kinds of systems on a simple, eventually consistent model. I mean, imagine your bank balance showing one number to you and another to an ATM, or an e-commerce site selling the very last concert ticket to two different people. For these high-stakes scenarios where a mistake leads to financial loss or security breach, you need immediate, strong consistency. Period.
And it's so crucial to remember this isn't about one model being better or worse. It's not strong versus weak. It's about having different tools for different jobs. The real art of system design is knowing which context demands which tool. If you take just one thing away from our time today, let it be this. The two models are fundamentally asking two different questions. Strong consistency asks, is the data correct? Everywhere, right now. But eventual consistency asks a totally different question. Is it on a path to become correct soon? And internalizing these two questions and really knowing when to ask each one is a huge part of the journey, from simply writing code to actually designing robust, scalable systems.
Now you might be thinking, okay, this feels like two extremes. Is there a middle ground here? And the answer is absolutely yes. In our next explainer, we're going to look at a fascinating hybrid model called read-your-writes consistency, which solves some of the most jarring problems of a purely eventual system.
Thanks so much for diving deep with us today. If this helped build up your intuition for system design, do me a favor and hit that like button. And of course, subscribe so you don't miss what's coming next. We'll see you then.